Okay, here we go. We have the second mole video, and we're going to just continue right where we left off with Avogadro's number, which is, we were just finishing at the end of the last video saying you take carbon 12, that particular isotope, and take exactly 12 grams of that, and when you count up the atoms, it's 6.02 times 10 to the 23rd. Just to satisfy curiosity here, I believe this number is known to 11 significant figures. So you could go much past that. In AP chemistry, we use 6.022 simply because most of our calculations are 4 and 5 significant figures, but most of ours are 3. So this is going to be perfect for us. All right. So we're going to do some conversions. You can convert a mole. So these are all mole conversions. You can convert them into a mass. I think you probably have that one down. Grams to moles, atomic weight, formula weight. You've done a lot of that. But you can also do volume if it's a gas. We're going to talk about that. And then number of particles using that 6.02 times 10 to the 23rd number. So we're going to walk you through a few example problems here. Make sure you get the overview of all 3 of those. Pause if you need to there. And then we'll start by doing mass to mole conversion. So you can see what I have written up there, grams to moles and moles to grams. You can go both directions. An example, convert 17 grams of oxygen gas into moles. So oxygen gas, that's the way oxygen exists out in the air. And you're going to convert that into moles. Now, just like all the other problems, the circle square method, the percent composition problems, both directions, there's a very step-by-step process that I want you to follow, and this is no different. We're going to use that dimensional analysis. So dimensional analysis, I always say it starts out really easy, especially when you have a problem with one number in it, because you just take that and you write 17 grams, and you know that's how this thing is going to start. And then you write your double-decker set of parentheses. Well, so far so good. You haven't really had to think that much yet. And then, as a matter of fact, the next step I think is easy too, because if there's a gram up there on the top, you're going to put the gram down there on the bottom so that they will cancel out, and that's a pretty straightforward step as well. Now, oxygen, you probably have this memorized. You have this memorized that oxygen is 16.0 grams per mole. We're going to use that one place to the right because we can go moles into grams. And you're like, what? Why is it 32 grams per mole? And that is because oxygen is diatomic. It's in the magnificent 7. If you've forgotten those, you need to go back and review which atoms are automatically diatomic. You know, this would have been the same thing if it was hydrogen, chlorine, fluorine, bromine, iodine, nitrogen, same rules. And you gotta know all 7 of those guys. Okay? Remember, start on element number 7 and make a 7 on the periodic table, and then throw hydrogen in. And that'll give you your 7 elements. All right. So, now you take the top number divided by the bottom number, and your stupid calculator is going to say 0.53125. And if you would put moles behind that, you'd only lose 1 point. But let's really work on getting that fig things down. I don't think there's too many of you out there who can't tell me that that number has 2 significant figures. So therefore, a chain is only as strong as its weakest link. This is my weakest piece of data. So I can only have 2 sig figs in the answer right there. Equals 0.53. And of course that leading 0 is important. It's not significant. You don't count it as a significant figure, but it is important because sometimes people don't see those decimal points. And when you get into the medical world, somebody's life could be at stake. This is actually a registered nurse who told me, you put that 0 or you lose your job sometimes. So I mean, it's a pretty big deal. And then of course, nice thing about factor label method is there's the unit for the final answer, moles, and that's what I wanted because you wanted to convert that into moles. So about half a mole. So you had your mole trap out there, and you got, no, I'm just kidding. That's morbid. That guy was so cute. The poop-eating naked mole rat was so cute. How could I say that? Half a mole. All right. So that's how you do the problem. And you get points for all of this stuff. Okay? If you jump right in and go, oh, it's going to be 17 divided by 32, and you get the right answer, congratulations. You get 1 point. Or, I'm sorry, 2 points. You get 2 points for getting the numerical right answer. But you're going to miss this one, 1. You're going to miss this one, 2. You're going to miss the units, 3, sig figs, 4. You miss the majority of the points. So tell the whole story when you're setting these problems up. Okay? All right, let's try another one. Let's take 2.15 moles of boron and then answer this question. How many kilograms is that? Okay, so you see there's going to be a little tiny twist at the end here, but we're going moles to grams, kind of, but you can't go directly to kilograms, so we're going to do it step by step. So this one's going to be a couple of conversions, or a couple of steps. So we go to 2.15 moles. All right, again, the first step is pretty easy. Second step, get the moles down there on the bottom on that double set of parentheses. Where did I get this? Well, I hope you know that by now. The atomic weights on your colored periodic table will convert grams into moles and moles into grams. Really almost should be instinct for you to grab that periodic table and say, this is how I convert mass. And that's what I'm doing right here. You already kind of possess that skill, but you got to show this dimensional analysis here, these parentheses. So we've got grams, we wanted kilograms, so we're not quite there. This conversion you need to know. A good scientist knows this. Hopefully, when I was gone, the substitute covered some of the basic conversions. And there's 1,000 grams in 1 kilogram. So now what you can see is you got to multiply the top numbers, divide by the bottom numbers. And by the way, these might look to you as 1 sig fig, 1 sig fig, and 1 sig fig, which they are if they were measurements, but they're not measurements. These are definitions. They're counting. How many kilograms? 1. That's an infinite number of sig figs. A lot of your math classes, you're not dealing with measurements. You're dealing with numerical truths and quantities that are not measurements. This is a measurement, okay? It's something that some people did some work to figure out. On average, a boron atom has 10.8 grams. There's some different isotopes, but we looked at all, we figured it all, did lots of studies of different samples of borons, and that's our number, and we're sticking with it. Over here, that's clearly a measurement that somebody is shooting for. Maybe you want to add that many moles to something, and you have a large amount, so you want to put it in kilograms. Well, it turns out, you're going to see, this is not a very large amount. I did want to show you here the purpose, since this is a two-stepper. The top and the bottom of these fractions, the numerator and denominator, they'll cancel out, okay? So the moles are gone, the grams are gone, and really, this is 1, if you think about it. These two things are equal. So you're taking 2.15 times 1 times 1 again, because these top and the bottom are equal. So all you did is times 1 times 1, and the the value of it is going to remain intact. And when you crunch those numbers, you will get 0.0232 kilograms. And yes, 3 sig figs, 3 sig figs, 3 sig figs. That 0 is not significant. That's just a place filler. This is 232 10,000ths. So you don't need those zeros except to show that it's a small number of kilograms, which kilograms are a pretty big unit. When you're using that in chemistry, you would need a lot of moles to add up to a kilogram, because we usually use grams in this amount. But this will help you a little bit with some of the math when that gets a little trickier. And you're going to get to practice these during workday tomorrow, Wednesday. All right. Now, our second one, which I think we'll probably just get started here for this second video, is the volume of any gases. And again, I might go a little fast here, so hit that pause if need be. Volume of gases. Liters to moles and moles to liters. That's the wheelhouse. That's the one we're going to use. Liters. There's lots of things we could use. Gallons, and then I would give you a conversion you could convert into liters. But this is how we want to do that. And the reason is that for any gas at STP, 1 mole equals 22.4 liters. Now, if you remember being in the class, some of you might be in class here today, look up at the front of the room that box that I screwed this box into the wall. And it's, you know, it has the dimension that's a little bigger than my head. You could get my head in there. My severed head would fit in that box. Hey, maybe that's what I want. Instead of my ashes, put my severed head in the box in the chemistry room. I'll have to make a note to myself for my will. Severed head. All right. These things just come to me sometimes. All right. So, you know what a 2-liter bottle of pop is. About 10 of those 2-liter bottles of pop, that is for any gas. If you have a mole, which we know how many particles that is, 6.02 times 10 to the 23rd gas molecules, or gas atoms, depending on which gas you're talking about, they all will do that. This was pretty radical. And it was the idea is that if you keep the conditions at STP, all right? So I know a lot of you, including myself, this was a big deal when I was a kid. The coolest thing you could get was an STP sticker. And I know that because I put an STP on my green. I had the high handlebars, the silver banana seat. Turns out you can buy a new one of these. This is called a Schwinn Stingray. And I was so happy to see this when I researched this. This was my absolute favorite bicycle. Which the end of the story is that this bike, it was really, I loved it. I had an STP sticker on the banana seat, and it was stolen. It was stolen from me in Burnsville. When I grew up in Burnsville, I've never been back. I'm sorry. We're gonna start the third video right now. It's STP.